the next talk, so I told you, we have different types of data sets, and we have different types of algorithms, and the question is always how to find the right algorithm for the given data set. Okay, so it involves a lot of experimentations, a lot of training, a lot of hyperparameter tuning for the algorithms and things and so on. So to that end, what we were working on is, can we automate this process of supervised learning? And I'm going to talk about automating supervised learning. Okay. Outline of the talk. First I will start with some motivation, and then introduce the framework AutoMOMML that we were developing for automating the supervised learning process, and some applications where we applied this framework, and finally summary and future work. So as you have seen, not only at Argonne, throughout the DOE level, we are faced with different verticals of scientific applications, starting from X-ray sciences to accelerators and material system engineering to national security. So there are different types of domains, and each domain has different types of data, and we are often faced with this question of how to extract knowledge from this from the different domain. So our overarching goal is to develop intelligent systems, such as sort of the high-level overviews shown here, that can understand different domains, learn from the data that is produced from the domain, infer to make inference, that is where the supervised learning is coming in, and generate new hypotheses based on what it has learned, and finally help domain scientists to do new set of experiments. So if we speed up this loop, then we can accelerate the scientific discovery. So that was our overarching goal. So this is again the same slide that you've seen in the last talk. How we are reaching that is through machine learning, and based on the amount of data that we have, we use deep learning or shallow learning, and there is a lot of given the amount of data that is produced at the accelerators or the high energy physics type of domains, we have recently started looking at deep neural nets. So machine learning, again, there are different ways, different types of approaches, and the particular approach that we will focus in this talk is, again, supervised learning. Again, so this example is, given a set of inputs and outputs. The outputs are the labels. It undergoes a process called training, and you generate a model. With that model, you give a new data, the new picture, and ask what the label is. So in a nutshell, this is called supervised learning. So how typically a supervised learning workflow looks like? So you take the algorithm, you give the data set, and you train, you do the training, and you see whether it is performing well on the training data set. If it is not performing well on the training data set, then you increase the model complexity and do this process again. So if it performs well on the training data set, which means that you have reached the best possible function, does it do well on the testing data set? That is, does it generalize well on the testing data set? So if it is no, then that means that the amount of data set that you have is not enough, because your testing data set distribution is completely different from your training data distribution, or the learning algorithm cannot generalize well with the given training data. So you go and collect more data, and then repeat this process. So when it performs well on the testing data set, you stop the process. So it sounds pretty straightforward, right? But often this is not the case. So 60 to 70% of the time, this is, I would not call this as a magic, but it's more an art, because there is no sort of a set of well-established scientific procedures that can get you there. So it's more like an art where you have to experiment with the different types of algorithms and start doing balancing or do hyperparameter search, and make the algorithm work for the given training data set. So that's why it's still making still developing machine learning algorithms or supervised learning algorithms is still considered as an art, and it is not a mainstream or it doesn't have any set of established scientific procedures. So exactly for this reason, NVIDIA wants to sort of train 100,000 developers in deep learning just for healthcare. Just for healthcare domain, they want to develop 100,000 developers. And that's for the same reason why Google's CEO want to do this in an automated way. He's so excited about automating artificial intelligence, which means that basically, can we automate the process of this supervised learning workflow or unsupervised learning workflow? Okay. So to that end, we were developing this framework called AutoMOMML, which stands for Automatic Multi-Objective Modeling with Machine Learning. So if you remember, this is the key idea behind supervised learning, where you have to balance the bias and variance. It comes from the fact that there is it's a no free lunch, which means there's no single algorithm that can perform well. So we have to customize the algorithm for the given data set. And the question that we are asking is, can we do this automatically? Okay, so this is the high-level overview of the framework that we are developing. So if you look at it, so you give the training data to the framework, and the framework start doing a number of steps, starting from pre-processing, correlation analysis, balance sampling, input importance, input selection, model selection, and finally, it will produce multiple objectives. So I say multiple objectives because in many scientific domains, it's not only one target value or only one target that you want to predict, but you have multiple targets. For example, you have in a material design problem, you want a material with the property A, B, C, D. Okay? So you want to build models for all those 4 properties. Okay? So the first problem that we looked at is with AutoMOMML is the mapping problem in HPC, right? So this is a common problem that we always face whenever we have an application or a new mission that is coming up, right? So we are faced with a diverse set of architectural landscapes, starting from heterogeneous cores, deep memory hierarchy, different types of interconnects, and diverse set of applications, right? So the question is always how to map applications to different types of architectures. So a key aspect in that mapping problem is performance models, right? So if you know how your application is going to perform on a given set of architectures, then you can optimize the hardware and software knobs and the application knobs in such a way that they map very well on the given machine, right? So that is the key. So you can develop performance models and then do some sort of multi-objective things like you want to find the trade-off between power and time. You can do that without running the code, right? So that is the key. You cannot run the application on the machine number of times to collect a large number of data points. So the idea here is can we run some micro benchmarks, collect the data, and then do the performance prediction on the application. Or you can also use performance models in more futuristic runtime systems where the performance models will help the runtime system or even operating system and compilers to identify the best set of operating knobs. Okay, so the key idea here is we develop some sort of microkernels. That microkernel characteristics will act as an input, and in the output, we want to model performance, power, and energy. So this is given as the training data to AutoMOMML, and it performs this automatically. And then, given the application characteristics, we want to find the predictions. Okay. So the first step, so we discussed this in the Q&A. How biased is our data set? So based on the microkernels, right? So this is the balance sampling phase, the first phase. I'm removing the pre-processing phase, so that is something straightforward. So in the balance sampling phase, so what you see in the color is a histogram of the training data. Okay, so this is for the performance response cycles per instruction on the micro benchmark. So y-axis is the frequency, x-axis is the cycles per instructions. And this is for the other objective, DRAM power, again, x-axis is the DRAM power in watts, and y-axis is the frequency. So as you have seen, so the micro benchmarks are small, so you end up with this biased training data set. And similarly for the DRAM power. So there are a lot of data points that belongs to this region and fewer data points in this region. If you use this training data set and give it to the learning algorithm without taking care of this, what will happen is that the learning algorithm is sort of biased towards this region. Okay? And your predictions will be bad here. It will be pretty good here. Similarly for this case. So you need to balance this. So one way we do balancing is we split this into number of bins, and then you do oversampling within each bin so that the number of data points which are shown in gray, that is after sampling. So after sampling, now you have sort of uniform distribution over all the ranges for here and here. Okay. So the next phase is input importance. So so one question that we often get is, okay, you do supervised learning fine, but we want to understand what are all the important inputs, or what is the sensitivity, or given these inputs and outputs, we want to understand what are the inputs that are important for predicting this particular property. Okay, so the classical sensitivity analysis, right? So you fit a model and then you look at the coefficients. But in the nonlinear case, or in the supervised learning case, when you use this algorithms to model nonlinearity, this is a little bit difficult. So what you can do is use a class of algorithms that can give you sensitivity. So here is the sensitivity analysis. Here the bar means relative importance. Okay, so read this as a relative importance. It will not give you a closed form analytical equation, but it can give you the relative importance of which input has a significant impact on this particular output. So for example, DRAM power, L2 misses and frequency, they are sort of the top predictors, whereas on the performance, the load and branching instructions and the floating point division instructions have a significant impact. So this also depends on the micro benchmark characteristic, but often gives sort of insights into what is important. So the next phase is a model-based input selection. Okay, so the idea here is you have set of all inputs. So also from this, whatever that is less than 5%, you can remove because they are not important, right? So you can reduce the dimension further here. So the next phase is input selection, where you want to make sure that the set of inputs that goes to the modeling phase really helps in prediction. So one way to do that is this recursive feature elimination, where you consider a set of inputs, so 5 inputs. So these 5 inputs are selected from this top 5 of this previous phase. Otherwise, this will be a combinatorial problem which you cannot solve in a reasonable time. So you take the top 5 inputs, top 10 inputs, top 15 inputs, and then you do 10-fold cross-validation for each one of them, okay, on the training set. And then what you observe here is this is an interesting property, right? So if you use all the inputs, so this is on the y-axis, you have the root mean squared error, and the x-axis is the number of inputs. If you use all the inputs, your error your error starts increasing after a certain point. So this is the sort of the overfitting case, and you want to avoid this, okay? And the best one is around this one, the 10. So after 10 inputs, whatever input that you use, basically, what happens here is the algorithm starts learning noise in the data, or it is trying to overfit. So you want to avoid the inputs that leads to that. So you can eliminate this and start, stay with this one. So that is the idea of model input selection, and this is all done automatically. But then after each phase, it produces a set of results. Then you can later take and introspect. This is one of the key component of the AutoMOMML. So hyperparameter tuning. So you have different set of supervised learning algorithms, and these algorithms have different set of parameters. And the default parameters, good luck. You can use it, you can see, and on the training data set, but often you have to tune the hyperparameters of those supervised learning algorithms. So to that end, what we developed is an a model-based or derivative-free optimization because you don't get derivatives out of supervised learning algorithms. So you set the hyperparameter, you can do cross-validation, get the output, and do this in an iterative fashion. So what we developed is sort of a model-based approach for the hyperparameter optimization. So here you take set of parameters and you fit a model, evaluate using tenfold cross-validation, and fit a model using that model, choose the next set of hyperparameters. And then you do this in an iterative fashion, and eventually we end up with the high-performing configurations. So finally, model selection phase. So each of this, so we consider a set of algorithms of increasing complexity. And for each algorithm, we tune the hyperparameters, as shown in the previous slide. And then we do model selection after that. So this is, again, on the y-axis, you see the root mean squared error, and the x-axis, different set of algorithms. So I have, this is a subset of algorithms that AutoMOMML currently has, starting from linear model. So that is always the baseline. K nearest neighbor, support vector machines, random forest, cubist, stochastic gradient boosting methods. So the box plots are from tenfold cross-validation, okay? And what you see here is the lower the better, and you simply perform a statistical test to select which algorithm is best suited for a given output. As you see here, right? So linear model is bad for both the cases, for the performance and the power. K nearest neighbor regression, support vector machines, they are not good even after doing hyperparameter optimization. For this case, for the DRAM power, random forest and stochastic gradient boosting, they emerge as a winner, whereas for the performance, random forest, cubist, and stochastic gradient boosting, all these three methods sort of emerge as a winner. So if there are more than one method that survives this process, then we take them and do an aggregation. So when we want to do prediction, we do prediction from each of this method and then take the average of those predictions. So this is how we started. But then the AutoMOMML is a sort of a generic framework you can then take and apply to different set of applications. And that's what we did. We started applying AutoMOMML for different applications, starting from APS data analysis to urban data analytics, all the way up to vehicle technology assessment. In all these domains, we have this sort of this common framework. You have the data set, you have a supervised learning problem, and we formulate that as an AutoMOMML problem where we want to find the right set of algorithms for the given data set by doing all the dimension reductions and model selection. So this is a case study. Simulation is a sort of a central theme in many of Argonne's science domains. This is on the vehicle technology assessment where we have 28 inputs for the simulation, starting from vehicle class all the way up to the number of engine cylinders, cylinder configurations, and et cetera. And there are 36,000 simulations we have to do on this study. And each simulation is not only expensive, but it produces 30 outputs. And the domain scientists are interested in modeling all the 30 outputs. So the outputs range from the power of the engine all the way to the battery efficiency. Okay, so this includes electric, hybrid, and conventional vehicles. So the interest here is not just modeling, but they want to minimize the number of simulations that they do. Okay, so instead of doing 36,000 simulations, the idea is, can we sample 1,000 simulations and learn from those 1,000 simulations, and can we predict all 36,000 simulations? And so this is the experiment we did with that data set. And what you see on the x-axis is the number of simulations, and on the y-axis you see the error. The error here is the maximum error. So that's the constraint from the domain scientist saying that I'm not interested in your average error. I want the maximum error to be less than 20% for any of the 30 outputs. Okay? So what you see here is the maximum error. And with 100 simulations, it's not enough because the error was up to like 85%. But then we brought it down less than 20% with 3,000 simulations. Okay? So this was eventually resulted in an order of magnitude savings because each simulation is quite expensive. This is not a throughput computing because they cannot run it on Mira or Theta because of the licensing issues. So this is the output from the variable importance. So this is another interesting thing they always ask. Okay, so what is, for my combined fuel consumption, which is the output, what are my my inputs? So aero, engine type, glider mass, so the powertrain. So these are the most important inputs that determines the combined fuel consumption. There is no analytical equation that can take them there, saying that, okay, these are the inputs. Of course, they have some sort of notion behind that, and they always want some sort of backing up using the data. Now they have that backup saying that, okay, with the data analysis, with the machine learning, we can say that these are the important factors. So the other interesting study that we did is to help the city of Chicago in finding restaurant violations. So city of Chicago send out inspectors to inspect restaurants if they violate sanitary conditions or not. And they have a data, they collected, so they have this violation data for the last 3 years, and we want to learn from the data, and we want to predict on a given day who is most likely to violate the sanitary conditions. So it's a pretty interesting study. So for that we pulled data from different portals, starting from business licenses, food inspections, garbage compliance, crime, 311 calls, sanitation compliance, weathers, and other informations. So these are the number of variables that we had to deal with, and this is data set size. So these are the results from the sensitivity analysis, okay, input importance. So what you see here, so before our study, they thought it's always the inspector. There is a bias. So there are some inspectors who are really strict, and they write a lot more violations than others. And in fact, if you don't balance the data, that's what you will see. But after doing balancing, and if you do the sensitivity analysis, then what it turns out is that the temperature, if you have a hot day, then it's more likely that some restaurants are going to violate the sanitary conditions. And the heat map of the garbage and burglary and sanitary conditions, this sort of captures the area in which the restaurants are located. So these things sort of became more sort of an indicator compared to the inspectors, which are, we sort of anonymized the inspectors, calling them inspector purple, brown, and blue. So those things went down. Okay, so this is the graph that shows how what is the business as usual. So the business on the x-axis you see the date. So this is we took the data, we split it, and then we sort of simulated, right? So we use the historical data, part of the historical data for training, and then the remaining data for testing. So this is on the test data, and the red is the business as usual. Okay, so if they set the inspectors the current strategy, so some of them are random, or some of them they have some internal algorithm to send those inspectors. So this is the red, business as usual. And y-axis is the cumulative critical found violations. Okay, so this is the data-driven approach where we use machine learning to sort of predict which restaurants will violate on a given day, and we sort of reorder the visits. And then we compute how many days we can predict in advance, and it turns out that compared to the business as usual, just for a simulated period of 2 months, on an average, we can predict 1 week in advance. We can predict, we can send and catch the restaurants that are violating sanitary conditions 1 week in advance. Finally, summary and future. So success in machine learning, in my experience, depends a lot on algorithms, using right algorithms, and using powerful algorithms depending on the data, and automation helps a lot. You don't want to do the same thing again and again, or you cannot just skip the hyperparameter optimization or imbalance in the data. So there are a lot of procedures that you have to apply before getting into the modeling process. Okay, so automation definitely helps, and I talked about a lot of cross-validation, which we didn't have time to cover, each and every evaluation, hyperparameter search or model selection, you have to do several folds of cross-validation. And each cross-validation is, again, expensive depending on the data set size. So computing power is an important factor. So we are in this three branches and try to use our computing power, different algorithms for learning and also for hyperparameter optimization, and also finally automation. So with that, I end this talk, and thanks for your attention, and I'm open for a few questions. Thank you. Yes.
So if your data set includes a parameter that doesn't really affect or have any correlation on the output, what does the model do with that data? Does it just ignore it, or?
In the variable importance stage, if you remember the sensitivity analysis, that parameter, that input will be at the end, down, less than 5%. And it will be automatically removed.
All right. Subsequent question.
Yeah.
The restaurant data that you showed,
yeah.
One of the parameters was crime. Doesn't that introduce a certain level of bias to your model?
So there are several questions on that front. So it's not only the crime; it's also the sanitary compliance. The garbage compliance. So the city sends out, or city makes an effort of the garbage collection in certain areas very well, in certain areas not very well. So that's also introduced sort of bias. So there is certainly bias, but we didn't introduce a bias. There's a bias in the data, and there is a correlation in that. We want to remove those factors and want to redo the exercise and see whether we can do the prediction. So that's something we are currently doing. Yeah. Other questions? Yeah.
It's sort of like a naive question, I think, just because I don't know anything about it. But is it possible to, if you have, say, one variable and you don't know whether the output might vary like linearly or quadratically or something, to include the variable twice, but then like apply a different function to it, or would that be two different runs? Or like say you don't have to vary just like the log of the whatever, or like the
Okay. In the shallow learning algorithms, if you know that so this is the input, and I know that this is a log of this input makes much more sense on the output, then in that case, do that explicitly, include that explicitly. This is called the future engineering process. Okay, on the other hand, if you move to deep learning, a lot of these things are handled implicitly by deep learning. But then if you know something about the data, if you know something about your input, try to include that. So don't let the algorithm try to figure it out, because eventually it will be easier for the algorithm to do that. Yes?
What do you feel about, I know this is more like algorithm but like specialized architectures like Iris or DN and Day or whatever, like those like specialized accelerators for deep learning and everything? Like how is it going to be, or will it be like integrated into like Mira and
Okay, so that's I mean, there will be, we definitely need accelerators. Okay, so a lot of the deep learning stuff. So once you move from shallow learning towards deep learning, you need GPUs. And there are a lot of studies now to scale these algorithms, not in the scale that people were talking before, but CPUs are too slow to do deep learning. You need accelerators, and what we do at Argonne is to run that on our visualization clusters, which have GPUs, Cooley and other nodes. We also have a DGX1 and P100s. So that's what we rely on. But I cannot comment on what our next machine will be. We don't know, or at least I don't know the specifics of that. But the machine at Oak Ridge has a lot of GPUs, and we are also using that machine to do some of our work. Yeah. Great, thank you.